in a parabola, the squares on ordinate-wise lines will be to each other as the lines they cut off on the diameter from the vertex. So that's saying the square on CE will be to the square on DF as the line AE is to the line AF. So I already wrote that to prove here. And what you'll notice is that this is basically y equals x squared, kind of, right? Because this is the diameter, and the ordinate-wise lines are kind of like your x, I guess. So CE squared, instead of saying, okay, so Apollonius obviously doesn't have variables, or like the concept of variables. So you can't have something like y equals x squared. You can have an area equals an area, or like a line is equal to a line in the sense that they take up the same amount of space. But you don't use it to preserve a relationship between two different geometrical objects in the same way we do now. So from Proposition 111, when we defined the parabola, I think I kind of alluded to this a little bit, but the thing is we have this parameter which is set up. So usually we have this relationship which we've constructed the parameter AG, or sometimes called the upright side, sometimes I call it the kickstand, such that a square on an ordinate will be equal to the rectangle AFAG. And AG is always some sort of like unknown in that instance, because we construct AG, whatever length makes that relationship possible, makes that square on DF equal to the rectangle AFAG. So I think before, this parameter was kind of mysterious, and this is the proposition where, at least in the case of the parabola, we can kind of step beyond that reference to the parameter. So that's pretty exciting. So that's enough background though. Anyway, so we want to get to this relationship eventually. So what we're going to do is we're going to talk about what we already know, which is what I just said. The square on CE is equal to the rectangle AEAG. That's by Proposition 111. And the square on DF is equal to the rectangle AFAG, also by 111. Square DF is equal to rectangle FAAG. Square CE is equal to rectangle EAAG, and equals have the same relationship to equals. So that's all that this ratio here is doing. And then over here, this is an unrelated step where you can see we have FA and EA on one side, and then we have FA and EA on the other side, but the difference is we've multiplied them both by the length AG. So my book, which is the Green Line Taliaferro translation, says that this is from Euclid 6:1, which has a construction something like this, which is that if you have like the same length of a base and you construct a parallelogram like this and a parallelogram like this, as long as they're underneath the same height, this could be whatever angle, and since all parallelogram areas are just base times height, they will be the same area. Or I should say more properly that not only will they be the same area, but the areas are to one another as the lengths of the bases. So if you have like a short base parallelogram under the same height, and then you have a long base parallelogram under the same height, the area of this one is to the area of this one as the length of this is to the length of that. Sorry, I kind of messed up that explanation. But anyway, so as FA is to EA, FA multiplied by this same height is to EA multiplied by that same height. So I'll put Euclid, I think it's 6-1. So now that we have these two steps, we can look at this right here, and we can notice that it is the same as what I've written on this side over here. So we can bring this side down in a substitution and bring this side down at a substitution. And now we have as the square on DF is to the square on CE, FA is to EA. And that is the same thing up here that we wanted to prove, because it's saying that the square on DF is to the square on CE as the length cut off on the diameter is to this length cut off on the diameter. So there you go.